In this video, we're solving problem 7.1.024 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to consider the following functions. We're asked to sketch and shade the region bounded by the graphs of the functions and then find the area of the region. Now, if we're entering our answers in WebAssign, we not only need to know how to sketch and shade the region bounded by those graphs on paper, we also need to know how to graph it in WebAssign. So my plan for this video is to show you how to sketch and shade this region on paper, and then show you how that translates to graphing on WebAssign. And then after we've done that, we will find the area of the region using the methods discussed in this section. Okay, so notice we've got functions of y here. I've got f as a function of y and g as a function of y. So it's implied that x is the dependent variable and y is the independent variable. So this is one x value, or this is one curve where x is a function of y, and this is another curve where x is a function of y. And we'd like to graph these and see what the region looks like, that region that's bounded by this curve and this curve. So let's do the bottom one first. It's actually pretty simple. I've got x equals negative y, and that's the same as y equals negative x. When y equals negative 1, x would equal positive 1. When y equals 0, x equals 0. And when y equals 1, x equals negative 1. So it's just a line that passes through those 3 points. It has a slope of negative 1. So it's roughly going to look like this. That's x equals negative y. Now we also want to graph x equals y times 5 minus y. Because it's written in this factored form, it's really easy to see that x will equal 0 when this factor equals 0 or this factor equals 0. And remember, x is equal to 0 on the y-axis. So this function equals 0 when y equals 0 or y equals 5. So our function is going to cross the y-axis at y equals 0 and y equals 5. And it may not be obvious when it's written this way, but if you distribute that y, you can see that we've got a parabola here. We've got x written in terms of y, the y is being squared, and it's a parabola. But since x is similar to y squared, that parabola is not opening up or down, it's opening left and or right. Now because the number in front of the y squared is negative, rather than opening to the right, the graph is going to open to the left. It's going to look like that. And since we know that x is 0 and y equals 0, y equals 5, and it crosses like this at x equals, or at y equals 0 and y equals 5, due to symmetry, that center line, that axis for the parabola, must occur halfway in between 0 and 5. So the vertex will occur when y is equal to half of that distance. So y is going to be 2.5 there. To find out the x value that goes with y equals 2.5, I will substitute y equals 2.5 into this function. So I'm thinking of x as a function of y, and I'm replacing y with 2.5 or 5 over 2. Personally, when I'm doing arithmetic, I would prefer fractions to decimals. Teach his own. Multiply straight across here, square the numerator and square the denominator here. You need a common denominator here. So this is 50 over 4 minus 25 over 4, which is 25 over 4, which is 6.25. So that means the vertex on that parabola occurs at x equals 25 over 4 and y equals 5 over 2, or if you prefer decimals, and I do prefer decimals when I'm thinking of numbers, when I'm thinking of graphing. X is 6.25 and Y is 2.5. Okay, so I want to go 6.25 units in the X direction and 2.5 units in the Y direction. So there's X equals 7, Y equals 2.5 is right here. Okay, so our parabola crosses here and here and here. It'll look roughly like this. And if the pattern continues, those two are going to cross over there somewhere. So I have sketched the line and I've sketched the parabola, and the region that we're looking for is right here. So it's easy enough to do on paper. Let's see if we can do the same thing on WebAssign. So I'm going to share my screen with you. Okay. So the first thing I want to do is, I think I'll graph the line first. So I'll grab this line tool, and then you just have to plot 2 points on the line. So I will plot 0, 0 as 1 point on the line, and X equals -1, Y equals 1 as another point on the line. And then if you look at the drop-down menu on the right, it shows that I've plotted 0, 0 and -1, 1. That's exactly what I want to do. Now when it comes to the parabola, I'll select the parabola tool, and I want the one that opens left and right. So I'm going to choose this little button on the right, and then I need to plot the vertex first. So I want to plot 6.25 and 2.5, which is kind of hard to do. We're just going to do the best we can. Won't let me, so I'll do that. And then I also know that this line, or this parabola, goes through 0, 0. It's not doing it. Okay, so I don't know how to clear that. Let's clear it. Okay, let's try again. So we're going to take this one, and then we're going to plot 6 and 2, or it's going to be 6.25 and 2.5. And then 0, 0. And see, that's incorrect because it automatically chose numbers on the grid line. So I'm going to go over here to the right and see how it says you plotted X equals 5, Y equals 2. Well, that was the only one it would allow me to choose. So I'm going to change this to X equals 6.25 and Y equals 2.5. That's the vertex that I want. So now I've got the correct parabola here. If it doesn't allow you to type that vertex because the X and Y coordinates aren't integers, just let it pick a nearby point like I did, and then go in and manually change it by typing in that point. So that's our parabola. And then I also want to graph the line. So I'll choose my line tool, and I just need 2 points on the line. 0, 0 is 1 point on the line, and when X equals -1, Y equals 1, that's also on the line. And I look over here and I see, yes, that's right. That's exactly what I want. And the region that I'm looking at is the region that is in between those two curves. It's this region right here on my paper. So I'm going to choose the fill here. You always want to do the fill last, and fill right there. Okay. Now, if you look at this graph, you can tell what the bounds should be when we're setting up our area integral. Now, remember, whenever we're thinking about these area integrals, we're always thinking about going from a top function to a bottom function, or a bottom function to a top function, or a left function to a right function. We're always thinking about those rectangles that came up when we derived the Riemann sum for the area under a curve and then for the area between two curves. And our rectangles could be vertical or they could be horizontal. So when we're looking at this, I think I want to draw my rectangles horizontally, because look what happens. If I draw these rectangles horizontally, the top function is that parabola the whole time, and the bottom function is the line that whole time. And as you think about all the possible representative rectangles, all of them have the same, not top function, but right function, and all of them have the same left function. Now, if I drew my rectangles vertically, this would be my top function for a bit, and then this would be my bottom function. And then once I got to x equals 0, I'd have to switch. The top function would still be on that graph of the parabola, but the bottom function would be the bottom half of the parabola. So I'd end up having to write two integrals if I used vertical rectangles. If I draw my rectangles this way, I only have to write one integral. So I'm thinking of x as going from this function on the left to the function on the right, and then we're adding from the bottom to the top. Since the width of this rectangle is a tiny vertical distance, that's delta y, the area will be the integral from some y value to some other y value of the x value on the right as a function of y minus the x value on the left as a function of y times dy. Okay. I know that you weren't able to see that because it's very small, but we're going to look at that again. It's x right minus x left, larger x values minus smaller x values, and then we integrate from y equals some value to y equals some other value. So let's look back at our graph here. When I'm looking at my graph now and I'm using my graph to determine what my bounds should be, I want to think about where the y values start and where the y values stop for this region. Now it looks like, well, and we know that this point x equals 0, y equals 0 is on both the line and the parabola, so we're going to start there. And then we keep going, and we've got a graph, and we keep going, and we keep going, and we've got this region until we get to y equals 6. At y equals 6, looks like x is equal to, well, x is going to be equal to -6. That makes sense since x is equal to negative y. When y equals 6, x equals -6, and that point x equals -6, y equals 6 satisfies both this top equation or this top function and this bottom function. So my bounds are y equals 0 and y equals 6, just from looking at my picture. And then I want x on the right, so that's the parabola, which can be written this way, minus x on the left. And you can simplify, that's 5y minus a negative y, so it's adding y. 5y plus another y is 6y. We'll evaluate this, and that will be the answer to the second half of the question. Now, if you're saying to yourself, how can I find those bounds without just looking at the graph? That there is a way to do that algebraically. If you'd prefer not to look at the graph first, if you're just looking at this graph and you're saying to yourself, how can I figure out that point of intersection? We can find these y values where the curves intersect algebraically. Notice at this point and at this point, the x values on our graphs are the same. The x values on this curve and the x value on that curve are the same. So if we want to find the y values where those two curves cross, we're going to set one of the x's, the x on one function equal to the x on the other function. So I'll take the x on the first function, which is this one, which is given by 5y minus y squared after we distribute that y, and I want to set that equal to x on the other function. Well, x is negative y on that function. And then we solve this quadratic equation for y. Since it's quadratic in y, I'd like to make one side equal to 0, so I'll add y to both sides. And then we can factor out a y. And now you have this times this equals 0. The only way that happens is if the first factor equals 0 or the second factor equals 0. And if we add y to both sides here, we get y equals 6. And over here, of course, we have y equals 0. So the graph starts at y equals 0 and it stops at y equals 6, which is exactly what we saw when we graphed the curve on WebAssign and then we just looked at the picture. Okay, so we've got these bounds and we want the area. So you take x on the right minus x on the left and you integrate from 0 to 6. Bring the 6 down, add 1 to the exponent, divide by the new exponent. Bring the -1 down, add 1 to the exponent, and divide by the new exponent. Evaluate from 0 to 6. Of course, 2 goes into 6 3 times. So I've got 3 times 6 squared minus 1/3 of 6 cubed. And then we evaluate all of this at y equals 0 and we get 0. So now we can do a little bit of arithmetic. We get 36 as our area. So that's 36 units squared, units being whatever x and y were measured in. Okay, let's go back to WebAssign and make sure that they like it. So we're here, here's our graph. I'm going to enter 36. And it's happy with that. So WebAssign likes that. Oops, that's not what I meant to do. I hope that helps you. Please let me know if you have any questions about using WebAssign to graph, or if you have any questions about the math. I would be happy to help you or happy to make you a video if that would help, if that's what you need.